Okay, so our next speaker is Habib Alizadeh, who will tell us about Hamiltonian fragmentations in dimension 4 with applications to spectral estimators.
Okay, thank you very much. Thanks for inviting me. And yes, I'll be talking about Hamiltonian fragmentation in dimension 4, and we'll see at the end some application to spectral estimators defined by Polterovich and Shelukhin. Oh, yeah, it's working. So I'll say a little bit about the history of fragmentation, and then we'll see an extension lemma, and fragmentation will be a consequence of that. And then our main result concerns hover approximating some C0 small Hamiltonians by some Hamiltonians that have like priori fixed support. And then at the end, we'll see some applications to spectral estimators that were defined by Polterovich and Shelukhin. So, so when I say like fragmentation, what I mean is that, so you have a Hamiltonian diffeomorphism and you want to write it as a composition of many other ones that have some desired properties. And these factors that are appearing, we call them fragments. And normally what we care about is that we can kind of control the number of fragments that appear in the fragmentation, or we can control the supports of these, or like for example, controlling C0 norm of these fragments in terms of the C0 norm of the original phi would be very useful. And we'll have some very interesting applications. So Baniaga, I think, was the first one, I guess, talked about fragmentation for Hamiltonians. And he proved some general statement about fragmentation of Hamiltonian diffeomorphisms, where he's able to support he's able to control the support of these VIs in the sense that if you're given a cover of your symplectic manifold, then any Hamiltonian diffeomorphism can be fragmented into the ones that are supported in one of the open subsets in the cover. But he has no control on the number of the fragments that are appearing, or any other information about the fragments. But if you assume C1 is small, then you can control the number of the fragments appearing. But these two first results are now by standard results. And in 80s, Fatih proved some general statement about fragmentation of volume preserving maps. But in particular for two-dimensional disk, it is about Hamiltonians. And so he's able to control the VIs in the sense that the size of the support of these VIs are very small, but no control on the number of fragments appearing or the C0 norm of them in terms of the C0 norm of the original one. And then later on, Leroux in 2009, he improves Fatih's result for C0 small Hamiltonians. And for C0 small Hamiltonians, he's able to control the number of the fragments appearing. Also, the size of the supports of these VIs are small. Later on, Entov Polterovich P prove the same kind of C0 small fragmentation for all surfaces. And they needed this to prove some C0 continuity of quasimorphisms. And Entov Polterovich P, they do control the number of fragments for C0 small Hamiltonians, the support of them, and also the C0 norm of VIs in terms of the C0 norm of the original one. So in the sense that if the C0 norm of the original one goes to 0, then C0 norm of the fragments are also going to 0, which is very important for this fragmentation, so you can use it to prove some C0 continuity. And also later on, I didn't write it here, but Seyfedini also used this C0 small fragmentation to prove C0 continuity of the spectral norm and surfaces. And in the same paper, Entov Polterovich P suggested to use theory of pseudo-holomorphic curves to prove some fragmentation results in dimension 4 at least. And so our result is about 4-dimensional polydisk for C0 Hamiltonians we control the number of fragments and the size of the fragments, and we use pseudo-homomorphic theory. And so the ingredients from theory of pseudo-homomorphic curves that goes into proof is the following. It's a theorem in Macduff-Solomon. So if you have a compact connected 4-dimensional symplectic manifold that has a symplectically embedded 2-sphere with self-intersection -1, it has no symplectically embedded 2-sphere with self-intersection -1. It has two homology classes with intersection 1 and self-intersection 0, and they're represented by symplectically embedded 2-spheres. Then what happens is that if you have two open disks inside a sphere, and you have a symplectic embedding of such a set into X with this extra property, then for any closed subset D in U and C in V, there is a symplectic diffeomorphism from a sphere times a sphere to a 4-dimensional symplectic manifold that is extending this iota. And we'll use this to prove our extension lemma. So X here is a sphere times a sphere, and our M is the 4-dimensional polydisk. And we think of M as the upper hemisphere times upper hemisphere inside X. And if you have a Hamiltonian diffeomorphism that is C0 small enough and supported inside this polydisk, compactly supported, then there exists a Hamiltonian diffeomorphism of X compactly supported in this set, and it extends your G, your Hamiltonian on this set. And what are the D3 and D1? So these two pictures are this upper hemisphere of the second factor, both of them. And so D3 is the region enclosed by these two red lines, and D1 is the green area, green region. So you can find a Hamiltonian that is supported in this region enclosed by the red lines, and it's extending your G in the green region. And the way the proof goes is just take your Hamiltonian, restrict it to this region, and then extend this restriction by identity, and extend it to the lower hemisphere also, and you will get some iota, some symplectic embedding as from such a set into X, where X now is like a sphere times a sphere. And then you just use the theorem, extend it to some symplectomorphism C2, but since it induces identity on homology by Gromov's theorem, it's just Hamiltonian. And you do the same thing in the reverse direction. You first restrict G on this region, and then extend it by identity to the region above, and this gray region, and then also the lower hemisphere by identity. Then you can use the theorem in the previous frame and get some C1, and then the C that you're looking for is this C1 C2 G inverse. So let's check if it has the properties. So let's say on the green region, C1 and C2 both are G. So C will be G. And outside of the red region, the region enclosed by the red lines, one of the CIs is identity and the other one is G. So the C will be G. It will be identity. So it does satisfy these properties. So our fragmentation result will be a consequence of this. So if you have a polydisk, then for any epsilon there exists delta and some n, such that for any Hamiltonian compactly supported in this polydisk, with C0 norm is smaller than delta, there are exactly n Hamiltonian diffeomorphisms supported on very small disks. I mean, disk with area small, such that G is equal to the composition of these GIs. So the proof of this goes like this, as follows. So you so this picture is the second factor, the disk in the second factor. And you split it into many strips, horizontal strips, by these black lines. And then around each black line, you do the extension lemma, and then you get this fragmentation. So G1 will be supported in this first strip, G2 in the second strip, and so on. But the last one, this Gn, is actually supported in this green regions. So the support is not a disk, but it's a union of disks which can be arbitrarily small, and they have arbitrarily small area. But the others are just supported on some disk with a small area. Note that we do control the number of fragments here. For C0 with small Hamiltonians, the supports have area very small, and I should also say that so this fragmentation is not C0 small fragmentation, in the sense that the C0 norm of these GIs are not controlled by the C0 norm of G. I mean, they're not even C0 small. And you can see in these strips could be very long. But we could make it C0. I mean, we could make them C0 small by just, for example, cutting the disk like that with very small black lines. But the number of fragments will increase, and also the C0 norm is not controlled by the C0 norm of the original one. But this is enough for what we need. So our main theorem is as follows. So X is a sphere times a sphere, and M is the polydisk again. And we fix a disk inside the second factor sphere. And then for any epsilon, there exists some delta such that for any Hamiltonian diffeomorphism compactly supported in the polydisk, with C0 norm is smaller than delta, then there exists some Hamiltonian diffeomorphism that is supported in this subdomain, and it has Hofer distance from G smaller than epsilon. So the proof of this starts with the fragmentation result, and once you fragment your Hamiltonian, so these GIs, if you remember, they're supported on some disjoint strips, and they have a small area. So these GIs could be like, there could be many of them, but the thing is that you can because they have like this joint support, you can move them around and partition them into groups, so that the sum of the areas of the supports of elements in one group is still small, but the number of these things, number of groups are kind of controlled. And note that we're not moving the last one, which has support that is not disjoint from the others, and just call these things just FIs, and then you can move the support of these FIs by conjugation into B by some H1 HIs that have a small Hofer norm, and the distance of the Hofer distance of this FIs from their conjugation is bounded above by the twice of the Hofer norm of HIs. So you can control this Hofer distance. And I should also say, I think this was originally the idea of I think Buchowski, Homilier, Seyfettin, I guess. Yes. And then let's move on to the application. I think I have 6 minutes. That's good. So in 2021, Polterovich and Shelukhin defined some functionals on the space of time dependent Hamiltonians for this specific four-dimensional symplectic manifold, which is a sphere times a sphere. This first one has area 1, second one has area A. A is a very small rational number, and these functionals are associated to some configuration of Lagrangians, and these Lagrangians are just these circles, this horizontal circles, times the equator of the second factor. And this KB, K is the number of these circles, and V is this area of this last strips, and the strips in the middle, they have equal area, and yes, and these functionals, they have like many interesting properties. I've listed them all here. I'll explain some of them that I need in the next frame. So yes, yeah, okay. So I should just mention that because of this property being Calovi away from Lagrangians, these functionals are not C0 continuous. So the Hoffer-Lipschitz property says that the difference between CKB of H and CKB of G is bounded above by the Hoffer norm of the difference. And the second property is the Lagrangian control property, says that if your Hamiltonian is only a function of time on the Lagrangians, then the CKB, you can calculate it, and it's just the average of your functional, of your Hamiltonian function. And these functionals are actually well defined on the universal cover of Ham. What you do is just take the path, the homotopy class of your path, and just choose some normalized Hamiltonian that generates that path, and define CKB of that path to be CKB of H. And this will be well defined. And Calovi property says that if your Hamiltonian is supported on some open subset away from the Lagrangian, then the CKB is just Calovi up to some constant. And controlled additivity, if the support of your Hamiltonian is inside some open subset away from the Lagrangians, then you do have additivity. So for any of the G, CKB of phi H tilde and phi G tilde is the sum of CKB phi H tilde and CKB phi G tilde. Yes. So my last frame is that is the applications of our result to the spectral estimators of Polterovich and Shelukhin. So if we define this invariant tau k prime b prime by the difference of these two functionals, then it's a well-defined invariant on the group Ham, because this group Ham of the polydisk is contractible, so it has pi1, 0, and these functionals do actually descend on the group Ham from the universal cover, and you have a well-defined invariant on this group, and we proved that this this invariant is uniformly C0 continuous. And the second application is so in this group, the group of compactly supported Hamiltonian diffeomorphism of this four-dimensional polydisk, the complement of a Hoffer ball does contain a C0 open subset, and we have some restrictions on the parameters because of they come from the technicalities of the construction of these functionals. And this like complement of a Hoffer ball containing some C0 open subset was first as a question that was first posed by Leroux. And at the end, we have this last application, which says the Hamiltonian, the group of Hamiltonian diffeomorphisms of this polydisk admit an isometric embedding of this infinite dimensional flat space where this group Ham is endowed with the Hoffer distance. And there are again some restrictions of the parameters coming from the construction of the the functionals. Yes, I think that's it. And I have 4 seconds, so thank you.
Thank you very much. Any questions?
So can you say something about homeomorphisms in this situation? So since you got a C0 continuous invariant, so do you get any information about C0 symplectic topology of polydisk?
Yes. So, well, I mean, but yes, I mean, not that I can say something new about Hamio, but the thing is that, yeah, so for example, so once you have the C0 continuity of this tau, they do extend to the closure of Ham, of course, C0 closure of Ham, but inside Homeo. But for example, like people study the simplicity of this question of this group, the C0 closure of Ham, and so in Polterovich and Shelukhin's paper, they do prove the simplicity, non-simplicity of the C0 closure of Ham of S2, and I mean they're able to do this because so this first sphere. So you can choose the second sphere as small as you want. You can take this A to be as small as you want, and this allows you to define the CKBs for a configuration of cycles here, which are like as many as you want, and they're like converging to the north wall. But once you fix the second sphere, the second A, and then you cannot increase this number of cycles and say something about non-simplicity of the group Hamio. I mean, yeah, I thought about this. I tried to kind of get around this issue, but things like yeah, still I don't have any new idea to approach this. But
Thank you.
thanks for the question.
Any more questions? Okay, if not, let's thank Habib again.